Dylan stay at the blacksmith shop, or more about specific heat capacity. This is my son Dylan. He's a bright 13-year-old with many talents and interests. He especially enjoys filmmaking and plans to pursue a career in the industry. Dylan knows a lot about science for an 8th grader. He knows that heat energy flows from warmer objects or substances to cooler ones until they reach thermal equilibrium. He is somewhat familiar with specific heat capacity, and he can calculate the amount of energy needed to raise the temperature of liquid water, given its mass and the magnitude of the temperature change. Dylan went to visit his Uncle Joe in Fredericksburg over spring break. Uncle Joe is a blacksmith. Dylan watched as his uncle made a set of horseshoes. Dylan learned that horseshoes are formed from very hot iron. Uncle Joe told Dylan that the temperature of a brightly glowing new horseshoe is about 700 degrees Celsius before he cools it in a tub of water. As we drove back to Austin, questions formed in Dylan's scientific mind.
Mom, if I have equal amounts of hot and cold water, and I pour them together, isn't the temperature going to be halfway between the original temperatures?
Yes, Dylan, why do you ask?
Well, water weighs 1 gram per milliliter, and the boiling point of water is 100 degrees Celsius, right?
Yes.
So I figured that the cooling tub contained about 10 kilograms of water. Uncle Joe said that each horseshoe is about 350 grams, or just over 1/3 of a kilogram.
Okay.
Well, shouldn't the water start boiling as soon as Uncle Joe drops a new horseshoe into the tub?
That is an excellent question, Dylan. The reason that the horseshoe cools so much more than the water heats up is that the specific heat capacity of water is a great deal higher than the specific heat capacity of iron. When we got home, Dylan found a periodic table that lists the specific heat capacities of the elements. He asked me if we could calculate the temperature of the water after it reached thermal equilibrium with the hot horseshoes. We know that heat energy is equal to the specific heat capacity times mass in grams times the change in temperature. We also know that energy is not created nor destroyed, so ignoring any heat energy from the horseshoe that might escape into the air, we can say that the heat gained by water is equal to the heat lost by the horseshoe. Putting those together, we get that the specific heat capacity of the water times its mass in grams times its change in temperature will be equal in magnitude and opposite in sign to the specific heat capacity of the iron times its mass in grams times its change in temperature. Dylan made a table of values, specific heat capacity values, masses, and changes in temperature, and what we're solving for is that TF, or our final temperature. Note that the specific heat capacity of iron is 0.441 joules per gram times degrees Celsius, and for water it's 4.184, so you see a tenfold difference there approximately. Here Dylan has plugged our values into the equation and then rearranged algebraically to solve for that change in temperature. So here Dylan has finished the algebra and come to a final temperature of 22.5 degrees Celsius. Now you can see quite a change from the initial temperature of 20 to a final temperature of 22.5, or a gain of just 2.5 degrees Celsius for that tub of water, while our horseshoe went from an initial 700 degrees Celsius down to 22.5 degrees Celsius. And you can see what an impact the difference in specific heat capacity has. I would like to thank Dylan McBride for helping with this educational photo story. I'd also like to acknowledge Learner.org, What'sCookingAmerica.net, Chemistryland.com, CircleU.com, and Florida Department of State websites for some of the photos.